Okay, I think we're on podcast 5 of Attitude Control. But when you think 5, they're mostly 35, 40 minutes long. So 200 minutes, it's a little bit more than 3 hours. It's just a little bit more than spending a week on it. I used to always say I'd spend a week on it, and then we never quite finished. So maybe I'm about on par with Classroom. We were on slide number 29 about 3 axis. Pretty much finished that off. And you can go into all kinds of there's some, like I said, so many interesting things about the propulsion, how you get things to geosynchronous, what's meant by geosynchronous slots, why bother in the first place. But we're talking about attitude control, so I wanted to stick with attitude control, and we'll talk more about geosynchronous, when we get there. But I would say in general, in engineering, as there's a reason we make things more complicated. These satellites are highly complicated. The orbit they're in is very hard to get to. It's very hard to stay in that orbit, so they need high performance propulsion when they get there. And of course, the antennas on the ground, as pictured on that photo, tend to be pretty big because you're going out 39,000 plus kilometers. And without getting into radio design, 1 over r squared is not in your favor compared to being in low Earth orbit, where the modern trend is now to put satellites in low Earth orbit. You're 500 kilometers away. Or even if you say, well, it's down near the horizon, so it's a little farther away, it's 1,000 kilometers away. So 1,000 kilometers versus roughly 40,000 kilometers, 40 times farther. It's a lot, it's a lot farther. It's 1,600 times weaker signal. And so you got to do something about that. You got to have 1,600 times more area in the antenna, or you've got to have a lot more solar panel area to make a lot stronger transmitter. So, it gets more complicated. And the trend that, I was one of the people who was, promoting since the 70s, being a person who likes to avoid complication, shirks from hard work, I guess, is, does it have to be that complicated? Space has an attitude that we don't go there. President Kennedy said, we're not going to the moon because it's easy. We're going to the moon because it's hard. And that created a philosophy in space that hard is better, which you do not see in, commercial product design. What you see in commercial product design, how simple can we make it and still satisfy the customer, because the simpler, the cheaper. So I'm not saying one is bad and the other is good, but I think we lost in our, excitement about making space do more, that, the also value of simple things that do less. And so, that we're looking at this satellite, which is kind of on the extreme side, along with the interplanetary probes and so on, at the extreme side of complexity. And, I was sort of wrongly characterized as saying that those satellites were going away. And I used to say all the time, that's not the way products evolve. Just because we know how to make things simpler and cheaper and so on doesn't mean that cell phone cameras did not kill off Nikon reflex cameras. There are people who what happens when technologies mature? There are more choices. And those choices can be simple for people who can get by with simple and don't have the budget or whatever their needs are, more casual. And there'll be super complex that'll become ever more, capable. And that's what we've seen actually happen in space. And it's not like you have to be a super genius to realize that. Just look at everything else in the world, how they have evolved. The car didn't kill the bicycle. Television didn't kill the radio. And despite the song, that video killed the radio star or whatever it was. So anyway, I want to kind of step back that's kind of an introduction to slide 30, which is, it's not really a trade-off, a table, doing the pros and cons. I have the pros and cons, but I really meant it to be more of a list of everything we talked about. Unstabilized, passive magnetic, passive aerodynamic, sun pointing spinner, earth pointing spinner, and those could be either, and then, earth pointing gravity gradient, which I don't consider particularly simple, but, I have my biases there from having, these scars. Sun pointing non-spinner, earth pointing non-spinner, non-spinner meaning, you're gonna have some momentum storage on board. and then the full three-axis stabilized being the most complex. The interesting thing about complexity is in the electronics world, we've swallowed it up. I mean, it's not complicated for you as the designer because you don't have to design the chip, right? The complexity is in the chip, and all you have to understand are the pinouts and, various other things. Sure, it's not simple, but you're not building a circuit with a billion transistors in it either. So, the older guys tend to criticize the younger guys as, not knowing, we don't, that I wouldn't say we anymore now that I am an older guy, but that, we younger guys don't know how to design an oscillator. But, we do know how to do a lot of other things that those older guys, I still get those kind of, basic tone of messages in my emails. These young people don't know how to do anything. Well, my experience working with younger people is that both in my company as employees and, with you guys as students is you know how to do things that I never learned how to do. And, again, I'm not a person who, very partisan at one point of view, other than the partisan point of view that you shouldn't have a partisan point of view. So I guess, but I actually think that there is a value to the way, my generation, let's say, of engineers operated by, by calculation by hand. And when we talk about heat transfer, when we talk about other things, I kind of say, well, the first thing you want to do is calculate it by hand to have an intuition about how it works. So anyway, what I was getting to there is that while I call three-axis highly complex, it's starting to become packagized, and you could just buy a three-axis stabilization system. You don't have to know very much about it other than essentially the pinouts. How do you work it? And you don't have to worry about when we did it, we had to worry about buying momentum wheels and how do you control their velocity. And there's millions of little engineering jobs that go into orienting them and building the structure to orient them because your system is only as good as the geometry of your wheels. Because when you command them to change, you have a model of what vector they're operating on. So you've got to do a lot to do that. And nowadays you can buy a 1U cube that's a three-axis stabilization system and you just figure, well, the hell with it. So, maybe it's not the most complex solution. It depends what's out there in the marketplace. It may be gravity gradient, which is very DIY, will turn out to be more complicated than three-axis stabilized, and people will say, why bother, to do anything else other than three-axis because, you can just buy it off the shelf. So then it comes down to, how much accuracy you can get from it, the pros and cons, how much it costs, that sort of thing. So, I don't want to read this whole chart for you. These are my own informal thoughts about the things that are pro and the things that are con for every one of these systems and things to look out for, And in the non-spinners, for instance, going to the third from the bottom and the second from the bottom, you're going to need a momentum wheel. And right there, they're expensive. For nanosatellites, they're cheaper, but they also have a problem that they vibrate, that they need power 24/7. If you ever shut it off, the satellite's going to start spinning in the opposite direction. And the wheel by itself does not stabilize. The wheel is a reservoir for momentum. So if the satellite starts to nose down, pitch down, you can spin the wheel in the pitch down direction to cancel that angular momentum of the body and bring the body back up and stop it, at wings level. What I think of, pointing straight ahead, whatever straight ahead for you is, straight along the velocity vector, straight down, doesn't matter. If you keep doing that because you've got a disturbance torque like gravity gradient that keeps pushing the nose down, you're going to keep spinning up that wheel. Sooner or later, you reach the red line of the wheel, and then what? Then you've got to have an external force, what they call unload the wheel, something that pushes in the opposite direction. In low Earth orbit, you might be able to get that from the Earth's magnetic field. And so turn on some sort of electromagnet, an electromagnet that, gives you an H cross B with the Earth's magnetic field and gives you a torque in the equal and opposite, in the opposite direction, and keep it turned on until the wheel is not anywhere near its red line anymore. Then there's some wheels that don't ever want to be driven to zero because their bearing system requires that the wheel be spinning, and so you're not supposed to go through the 0 point. Many of them are nonlinear going through the 0 point. So I mean, it takes a lot of thinking. It's much easier to just spin up the body and the hell with it. It doesn't cost power. It doesn't take anything to do it. Then, of course, you've got to read the velocity of the wheel to know how much you're speeding it up. So you need some sort of a tachometer, usually a laser, and there's a dot or reflective dot on the wheel. It gives you a pulse every time the wheel goes around. There's a lot of engineering if you're going to homebrew it, if you're going to DIY a system with a momentum wheel in it. Whereas, again, you could just buy the box. It's a little sad in a way, because, the joy of, like we were talking about with the chassis. I mean, you guys want to build the chassis. So, and I appreciate that. But, the trouble, what happens in the real world, let's say, in the outside world is like, yeah, but I have to have it tomorrow and I'm only going to pay for 3 of you. And then you're driven to what's the fastest way to get this thing done. And it's always like, okay, buy this, buy that, and, my father was a construction guy, and he started building houses and apartments after World War II. And back then, carpenters built frames, with, by hand, with the little boxes that make the angles and so on. And by the time he got older, you couldn't do that anymore because the prefab of framing had become so universal, and these were factories that stamped out gazillions of these frames and delivered them in a big truck, and it was just not worth the labor to pay union carpenters to custom build one frame after another, all identical. The ceiling, the roof framing, and the wall framing, and all that sort of stuff. And what he said to me, was that frames you buy are fine. But it's kind of sad because all the carpenters have disappeared, and all you have now are people who know how to, use a nail gun to just nail it all together. And he said construction sites have become, bring in the truck, drop off the frame, and nail it together, and all you hear is the sound of trucks and the sound of, pneumatic nail drivers. And in a way, that happens to a lot of engineering. So the disadvantage of that is that a lot of houses look the same because there are only certain frames available in the catalog. And before that, all of his houses looked a little bit different because they were custom built and, the lot and the blah, blah, blah. And he said, all that's gone away. We just level it all out and build one house after another. And so you have, various, let's say disadvantages to, the prefab. And I'm just saying, we see that in everything. It's just the way the world works. And, we're seeing that in automatic control also, and I think you're seeing it in your shopping. And maybe that's going to de-emphasize the DIYs like we're talking about, aerodynamic and, gravity gradient. These are the things that radio amateurs and other, small-scale hobby builders, would pull out of their hat because they were long on brain power and short on money, basically. Okay, to get off of that subject, slide number 31 on feedback control, I mean, we've seen this. So why am I showing it to you again? To talk a little bit about the control algorithm, just for a quick sec, which I kind of talked about before. So if you go to slide 32, a 0th order angle controller, I mean, I almost don't like to get into what is called a 0th order and a 1st order because different people, adhere to different religions there. But let me say that when I mean 0th order, I'm in the slide anyway, because I don't even use the terminology. I mean, pedantically, always the same either. But all you're looking at is the position. When you have a spring, the spring, and you have a mass, and the thing is traveling on some sort of a rail, like you do if you're lucky and you had high school physics class with a big lab and you could do the waves and, the wave tank and all that kind of stuff to see interference patterns. And I was lucky enough, even though I went to, a super large, edge of the urban development public high school, they happened to have built a science wing. And for a few years that I happened to have been there, I guess it was inspired by, the moon race and Apollo, and everybody was worried about training little techies. And by the 70s, when I got to high school, these science wings were everywhere. And the interesting thing about my high school, when I go back to Ohio, they tore it down. It's gone now. So to bring back the classic look, the high school is very old, and they cleaned it up, and it looks like Brown University now. I mean, it has that kind of very classic brick architecture. But at that time, we had a science wing, and we had all the fun tools. And we would take, stroboscopic pictures of falling steel, balls to measure G by ourselves and all that kind of, I thought it was fun. I really enjoyed it. So one of the things we did was you put a spring and a mass on a rail, and the mass can move back and forth on the rail, and then you pull it and you strobe it and you make a graph of the position and the velocity, if you can get it, which is not that easy, and then you see the sine wave and the cosine wave, which is exactly what I drew, on this graph. So what happens when you have a perfect spring and mass? The spring is sensitive to the displacement from its 0 point. Every spring has a 0 point where it's relaxed. So then you pull it, and you're bringing it plus x, let's say, from its 0 point, and it creates a linearly increasing restoring force. The further you pull it, the harder it pulls back at you linearly. And if it compresses the spring, it does the exact same thing. And an ideal spring would behave exactly that way. The force is equal to the displacement times a negative constant. It's always the negative number in feedback control, because whatever the thing is doing, you want it to do the opposite. You're trying to pull it back to the equilibrium point. So your gain factor, classically in automatic control, is always a negative gain factor. So that is, a standard way of thinking of things that we always, because when you think about it, if you pull the mass to the right, to the plus x, the spring is going to develop a force toward the minus x. So it makes sense that the spring constant is a negative number. If you do that, as you probably know, with a undamped, frictionless mass and spring, it will oscillate forever. And you can think of that as, in a way, a pendulum. Gravity pendulum is the same thing, where gravity is the spring. So that's a zeroth order controller. And that is basically gravity gradient stabilization. So every zeroth order controller is, if you can stand it, it won't, just like your spring, it's not going to go to infinity. It's going to oscillate with a certain amplitude, which in this case depends on your starting amplitude. So many gravity gradient satellites just oscillate back and forth 10 degrees. They look like a pendulum. If you can live with that, it's fine. If you can't live with that, you got to do better. And how do you do better? You go to slide 33, and you go to a first order angle controller. Okay, I said angle. In the case of a stabilization system, it's usually angle. You're trying to point straight down. And then you measure your error according to the angle error. You're trying to point at the sun. So, and you might have two angles, a left-right angle and a north, up-down angle. But anyway, it applies equally well to a left-right controller. A first-order controller can sense the position and the velocity. So when the thing is moving really fast, it tries to slow it down, another negative. And so you mix those two, feedback constants so that you can get a behavior that eventually drives itself to something like zero. It won't ever really, it's, asymptoting to zero, but who cares? When you get down to, it's not that you're going to say, oh, well, you can add order controllers to infinity. You will never get to zero without damping, but you don't care. Once it gets down to the precision, less than a pixel of blurring, you're done. So the only question is, how long does it take it to settle, to that point? So, this is the interesting story that I always tell about, bicycling. I wrote in the homework question, is that this is the behavior of drivers. This is the behavior of human beings. Human beings are very good at sensing position, and they're pretty good at sensing velocity. My mother used to always tell me when I was learning to drive, if you're trying to turn left against traffic and you can't decide whether to go or to wait, look at the car that's coming at you, and if it looks like it's going fast, don't go. That's interesting advice from a totally non-technical, person who taught German, English, and history. Because what she's saying is, if you perceive it as going fast, it's either going super fast from a distance or it's pretty close to you, right? Because your perception of velocity has to do with, things like how fast the size of the object is changing in your eye. So what she was saying is that your eye can determine the position and the velocity. And so it can be far away, but if it's moving really fast, maybe you don't want to try to make that left turn. And, if it's not moving very fast, but it's right there in front of you, probably not a good idea to make the left turn. So anyway, that's the second order rule. The first order rule is, when in doubt, don't go. I used that one on my driving test, and I actually got 5 points taken off because I didn't go when I could have gone. Oh well. So anyway, the first order controller is a lot better, and it's the way people drive. And therefore, when they veer out of their lane to miss you on the bicycle, you'll usually see them cross over back into into your lane. And like I said in the homework, bicyclists take that as a sign of aggression. I take it as a sign of being a first order, controller. If you had a third order, you might, depends on your gains, you might be able to not cross over the line and asymptote back to the line after the disturbance. The bicyclist is a disturbance. It causes you to veer to the left. And then you want to get back to your lane, so you're controlling yourself from a disturbed position back into your lane. And what do you use to do that? You use your position. How far away are you from the white line, what they call the fog line, the white line that marks the right-hand side of where you're supposed to be driving, and how fast you're approaching that white line. Obviously, if you're coming at it pretty fast, you're going to, you're going to turn the wheel back to the left. That can go unstable. Obviously, people get in accidents because they make an overcorrection. Then they see they're going too fast, and so they correct back the other way and, spin out the wheels or whatever. Anyway, that's what I got to say about various order of controllers. On to slide, these are all like, little quick facts. 34, environmental torques. Okay, we've talked a lot about disturbance torques. So, environmental torque's a more polite way of saying the same thing. Whether these torques are control torques or are disturbances, that's why, the polite way to say it is environmental torques. You have an aerodynamic environmental torque and quantified it at this point a little bit, at least quantified the force. It's a force at a distance, that's going to make the torque. So the question is, how separated is that torque from the center of gravity of the satellite is going to determine but anyway, that could be your friend. That could be your stabilization force. Or it could just be, this is screwing up my gravity gradient system because I know that gravity gradient is very weak. And when somebody comes to you and says, I want to launch a satellite off the space station and then gravity gradient stabilize it, you're going to immediately be, hey guy, let's check how big the gravity gradient force is compared to how big the aerodynamic force is. And at the height of the space station, you're going to find out that the aerodynamic torque on just about anything other than a basketball, and a basketball isn't going to gravity gradient stabilize. Well, it could. The moon is gravity gradient stabilized, and it's a basketball, but it has a very odd mass distribution. Part of the moon is heavier than another part of the moon. It's not homogeneous. So you could do that. You could build a sphere, which would not have any aerodynamic torque on it, and you could totally weight one side of the sphere. It would probably gravity gradient. I don't know if anybody's ever done it. Probably, maybe. So anyway, let's say at least you'd have to think about it. You'd have to think about the fact that aerodynamics is going to play a large part. And like I said, if you want to do a wheel-stabilized or spin-stabilized satellite, to make it stable spinner, you have to have a disequal mass moment of inertias. If you spin a basketball, you can't guarantee what axis it's going to end up spinning on. And the body will evolve over time because you never get a perfectly, set up spin. And so, with a little bit of aerodynamic force, with a little bit of asymmetrically of either the mass distribution or the aerodynamic distribution, since you never get a perfect sphere, the spin axis will slowly change because there are torques on your gyroscope, right? But if you have a true gyroscope that has a lot of mass on one of the, axes, the spinning axis usually, it's going to spin stably on that axis. And actually, one of my homework problems in control theory was to take an object that had, 3 different moments of inertia, small, medium, and large, the 3 different dimensions of a block, all different, which would basically be a piece of paper, right? Because, one axis is the x-axis, the y-axis is longer, and then the z-axis is extremely small. And the question is, what are the stable, spin states of a piece of cardboard, let's say? So things will tend to eventually, with a little bit of damping or a little bit of, disturbance torque, spin on their maximum moment of inertia tensor. And so you're going to do that, you're going to create a maximum moment of inertia tensor, which is basically like, the skater with their arms sticking out on both sides of them and maybe little dumbbell weights on the end of their arms, or maybe other skaters on the end of their arms. And you're creating a gravity gradient stabilized satellite, but you didn't mean to. And the gravity gradient is always going to try to pull your partner skaters toward the Earth or away from the Earth, with you at the center of gravity. And that's not what you wanted to do on the skating rink. You wanted to be horizontal on the ice. Well, luckily, gravity gradient is pretty weak, so you don't really feel that when you're skating, but when you're in a satellite, you do. And so it's going to take your spin axis and constantly try to warp it. So gravity gradient is weak but relentless, and it becomes, a disturbance torque. So stray magnetic fields, we talked about solar pressure, leaks and outgassing. These are things people don't usually think about. But, the little boat that you make that goes forward in the bathtub, you put the bar of soap on the back of some floating object and it propels itself, is because the soap is basically, let's call it outgassing into the water. And because the boat is in front of it, the outgassed, the pieces of the soap that are coming off can only go in one direction behind, and that pushes the boat forward. Well, if you get a leak in a propulsion system, with 10,000 psi nitrogen in there, that's your biggest torque, man. And that's just going to ruin everything. So you got to think about even a very tiny amount of outgassing, will disturb, the attitude of your satellite. So then torque noise is not really a disturbance torque. It's a vibration, but it's a vibration to think about. So, then there's, thermal flexing. This has always been a problem in big satellites, that the solar panels, like with Hubble, the solar panels go into the sun, and then they go and when they go in and out of the sun, they get hotter and colder, and so they shrink and expand, and that changes the mass moment of inertia. That changes the center of gravity and the mass moment of inertia. And so, it causes a disturbance. And, obviously if you get hit by an object, that's not a good thing, but it has happened. And, that's a kind of maybe it's going to happen more and more now that we're putting a lot of objects in space. Anyway, threw it in there for the sake of completeness. Okay, these are the sensors and actuators on slide 35, the green slide. Sun pointing, what we tend to use, magnetic torque coils and or, rocket motors. And then a momentum wheel if you have a non-spinner. Those are your actuators. Those are the things that do the work of establishing that stabilization. And then what are you using for your sensor to plug into your algorithm? Well, it all depends. If you're pointing at the sun, you usually have a sun sensor. So then I put down plus Earth or star sensor, because if you're pointing at the sun, how do you know how fast you're spinning? If you're spinning and you want to spin at whatever, you're pointing at the sun like I did because you want the solar panels pointing at the sun. And the other reason was, in that particular case, the astronomers wanted their instruments to never see the sun. So it was a very complementary relationship, but they also didn't want to spin faster than a certain rate, in that case, half an RPM. So how do you know what rate you're spinning? Because the sun is basically, you can think of it as a uniform disk. So then you need some perpendicular thing. So one of the perpendicular things you might think of is, look at the Earth. Because as I'm spinning, I'll see the Earth going, around. Maybe, depends where you are in the orbit, where the sun is, at noon, you're not going to see the Earth. So it's not a perfect, but maybe you don't care. Maybe if once in a while you see the Earth, your velocity, angular velocity not changing very much. Okay, another thing to do is to sense a star. And what you'll see when you sense a star, the trouble is you'll sense a lot of stars. Every time a star goes by, you get a blip. And depending how bright the star is, the blip is a different height. So as you're spinning around, you'll get a pattern of blips that repeats once per revolution. So all you need is sort of a pattern recognition thing that will lay one over the other and say how much displaced in time was the second one compared to the first one. That correlation will never be exactly perfect because the satellite's attitude is never exactly, but it's close enough that as long as you accept a little bit of out of kilterness, of course, when you accept a little bit of out of kilterness, you lose time resolution. I mean, if all you care about is turning at a half RPM, it's probably going to be fine. But just to point out, it's a little bit of, the Heisenberg uncertainty principle, bites you also there. So you think a lot of these things are super trivial, but, if you want to do a super precise mission, like an interplanetary mission, you've got to navigate to Titan. Very small errors over billions of kilometers, kind of add up. So you end up worrying about, things that are just like, really? We have to worry about that? Just like GPS, you may have heard the story, has to worry about the fact that it's in orbit and it has an orbital velocity relative to the Earth. And so its clocks, even though they're identical to the cesium clocks on the Earth or very close, do not keep time the same way. They're running slower because of relativity. And someone wrote a paper on that when GPS was first getting underway, and all the other scientists said, this guy is, crazy. We're nowhere near the speed of light at orbital velocity at that altitude is like 5 kilometers a second. And yet he showed that it would be a significant source of position error for a GPS if you didn't correct for the relativistic effects on the... So, I mean, a lot of guidance people heavily get into that. These very like first, second, third, fourth order effects that over long integration times can make a difference. So, with the passives like the gravity gradient, you could almost say I don't need a sensor. You only need a sensor if you care if you're pointing up or down. And then with the 3-axis, you're definitely going to need, nowadays we're getting to the point where we take pictures and recognize what's in the picture. But it depends, what you're taking pictures of. If you're hoping to take a picture of the Earth, and, you can kind of interpret that to get your roll angle, let's say, relative to actual Earth north. But if your camera doesn't see the Earth, you're kind of out of luck. So, more typically, we use a star sensor, to see, to photograph, in a sense, the star field, match it up with a memorized catalog of stars, and recognize, what your attitude is. And maybe sometimes on Zoom you've seen I have a little telescope, which I bought for, a few $100, a Celestron, little amateur, I knew nothing about telescopes, and so I got one so I could play with it on the roof of my condominium here in Rome. And it has that. So I bought it. It's a telescope for idiots. You point the thing at 3 different stars, which you don't even know what those 3 stars are, and it measures the angle in between the 3 stars, and it says what 3 stars out of all the thousands of visible stars have that angle relationship. Okay, it knows what the 3 stars are, and it says, okay, therefore your tripod is oriented in this way. You also have to tell it what time of day it is, and what time zone you're in, and you also have to get the tripod fairly level. It has a leveler in it. But it's highly reliable. Pick any 3 stars that are visible to you and drive the thing from one to another. It'll tell you, okay, go to star 1, go to star 2, go to star 3. That's exactly what a star tracker does, only it doesn't make you move. It's a wide field of view camera. It sees all 3 stars. It sees a lot of stars. And it says, given this mapping, we must be looking in this direction. It's actually a pretty simple idea. We built one ourselves at AeroAstro. I didn't do it, but it was something that a small company, 2 people, managed to build it in a few months. It was quite amazing to me that they did it. But it wasn't the super type of accuracy that you would get with Hubble, but it was adequate for fraction of a degree pointing. Okay. Gadgets you'll need to create. This whole extra section is I would have to say almost optional, except you guys are building a satellite. So maybe you need to know it. But when you think about it, how do you test an ACS? It's, to me, the most difficult system on the satellite for various reasons. I mean, you've got to know everything about the satellite. You have to know the mass distribution, how it changes with, with temperature and blah, blah, blah. Vibrations. You're the guy who has to worry about, is there anything magnetic on the satellite? Measure the mean magnetic moment of the satellite and how it changes when we turn the radio on, when we turn the blah, blah, blah. The payload, what kind of moments, how do I going to compensate for that? You're a satellite designer in a box, and then you're also have to do this very hard control system. So obviously you can't test it on the ground because you need torque-free motion, with no resistance. I mean, torque-free is one thing, and then no damping, no air resistance is a whole other thing, and you don't have either one of them on the ground. What if you build a gravity gradient satellite? How are you going to test it? If you say, well, this is an adequate amount of damping, how do you know that? Well, you make a dynamic model of the satellite in your computer, which mimics all the mass properties, and the dynamics of the internal workings of that satellite. Hopefully there aren't any, you know what I mean? Hopefully it's just a rigid body. And then you need what I call the universe model, which is what am I looking at around me? Where's the, as a function of time, where's the Earth, where's the moon? Luckily, you don't have to create all that. People make that stuff, but you got to be smart enough to use it. And that's not so trivial either. In modeling the Earth's magnetic field, if you have magnetorquers, electromagnetic, electromagnets, I don't know why I'm having trouble with that word today, electromagnets, you got to know what's the external field. I mean, when you're doing the simulation, do I have enough time in the Earth's magnetic field when it's pointing in the right direction with this size electromagnet to flip the satellite over and stop it before, let's say, I go over the North Pole and I don't have the field, I don't have the field vector that I need in order to create that torque anymore. So then the drag model, and if you have a star tracker, you need a star map, that tells you where are all the stars at every minute, every moment of your orbit. So then you've got to model your sensors, because your sensors do not tell you exactly what the attitude is. They tell you what the sensor is reading, which always has some error, some lag, some digital noise in it. And so you've got to have a model of how do my actual sensors that are on my actual satellite, what are they going to tell me? What's the signal coming out of them, including the fact that they're never quite aligned. You could say, well, they are aligned. But then if the CG isn't exactly where, or the mass moment of inertia, we never know exactly where those mythical vectors are. So you may put it where you think the CG is, or you may put it where you think the maximum moment of inertial tensor, is. I mean, the maximum moment of inertial axis is, but you really don't know that number. And it could change during the flight if you deploy something, if you use a propellant, et cetera, et cetera. Then you have to write the control algorithm. That's actually the easy part, a few lines of code, done, right? And then, of course, writing those few lines of code could be a lot of analysis to pick out the gains. But usually you get in the ballpark with the gains and then you play with your model and see if you like it. Put in the disturbances that you think you're going to get. And then somehow you want to test it. And one other little thing that I put in here is the actuator, this little graph at the bottom of the page. You want to command a torque impulse, a force that's at a distance for a certain amount of time. That's square wave. That's what you want. But that's not what the electromagnet is going to do, because electromagnets, when you first put current on them, there's going to be an inrush, of current. When you first put a constant voltage across it, there will be an inrush of current while you're building the field, and then it'll asymptote out. That's not what that violet curve is the opposite. What it's saying is if I turn on a thruster pair to get a pure torque, the thrusters don't go on when you open the valve. I mean, there's some lag time to get the propellant into the catalyst bed or into the combustion chamber, whichever one you're using, and start to react. And even then you don't have any force, because you've got to fill the vacuum of the combustion chamber before you'll actually get the flow that you want out of the sonic nozzle. So there's a time delay. And then when you shut off the valve, modeled by the vertical red line going down, okay, I'm done. It's still, there's gas in the, there's combusted gas in the chamber and there's vacuum outside. It's going to keep coming out. Even if the valve operated magically, instantaneously, which it doesn't. And the valve itself doesn't go from state open to state closed. It's got a time constant, usually a millisecond, when it's in between the two. So it's kind of, that's your actual actuator. So you want to have that as part of, so to put it all together, if you're building from scratch a fairly sophisticated, you've got thrusters, and you've got sensors, and you've got star trackers, you've got a major problem. And in a big, problem not in the sense of a disaster, problem in the sense of a difficult engineering problem that's going to take time, people and money, which is actually, my next slide, 37, is just a bunch of people and gold. Because in the end, when I've worked on these projects in big companies, you have hundreds of people working these problems, modeling the sensors, modeling the actuators, figuring out the master. It's not like you do it as a homework problem. You have a team of people, and it's typically hundreds of people, and they'll be working on that problem for years. And and they need the sensors, they need the actuators, they need laboratory space. And when you think about what it costs to employ one person, nowadays, $200,000 a year, $250,000 a year minimum, including the overhead of the company. If you have, 4 people, that's $1 million a year. So if you have 40 people, that's $10 million a year. And, so you just, take it up from there to maybe $25 million a year in staff expenses. And so you're going to buy yourself, $100 million control system. So I had to get my brain wrapped around that, after having been, a measly student, getting by on, being a TA, to get my mind wrapped around the fact that to solve the problems that we were learning to solve in graduate school as homework assignments took $100 million, and a big team. I got into a couple of those big teams. Even in thermal design, 100 people is normal for, big complex satellite when you're in the design analysis phase. Okay, so there's, various ways that we do this. And the one that we mostly do is, what I call battling computers. You've got one computer that's the controller that's running your control algorithm. That'd be the controller in your satellite, the board. And then you've got the plant, the thing that's modeling, the satellite. And it's got the sensors in it, it's got the mass model in it, it's got the universe model in it. The plant is the complicated thing. And so the plant is doing whatever it's doing. You give it initial conditions. It's spinning at some rate and it's pointing in some direction. And those sensors send the signals back. Here's what we think those sensors would be seeing spinning on this axis, at this rate. And the controller reads that and uses its algorithm to say, okay, if you're in that situation, here's what I want the thrusters to do. And then the plant says, okay, we're doing that, and here's the evolution of the sensor signals. And so that's your battling computers. And then eventually, the plant is still there, and we take the controller out of the loop and use the actual satellite's microprocessor, which might be slower, which might have fewer bit resolution, which might only look at that problem because it's being time shared with other problems. And all those things add, instabilities to the... And okay, does this work? If you work at a super sophisticated lab on slide 39, like JPL has one of these, they have, quote unquote, friction-free platforms that you can put a satellite in a vacuum chamber with a simulated, it's like a Hayden planetarium. They simulate the sky, stars, moon, sun, earth, and, they make up for the friction, by knowing what the actuator command is. So it, of course, isn't actually friction-free, but a computer is simulating as if it were friction-free. And, very few people have the money to do that. And even the people who have the money to do it, not always worth actually doing it. So what we really do is, on-orbit tweaking. We do the best we can with the various simulations, launch the damn thing in a mode, that's relatively simple, that we know we can at least get the satellite in a safe attitude. Then start turning it on. You always wondered, they say it takes a month or 3 months to get the satellite checked out on orbit. It's like, why? I never understood that. Didn't they build it on the ground? You know what I mean? But part of it is this. Part of it is, okay, the first time you're ever going to really use your attitude control system is on orbit. And I worked on a Swedish satellite that had some sort of controller. I didn't work on the controller. We were doing the radios for it. But being a control guy, I was a little bit interested. They had a red button, literally red button, at the control panel, which would do nothing but swap the sign of one of the feedback controllers, because it was so complicated, between the various fields and how electromagnets work. And they'd had a few errors and they were just afraid that they had the sign wrong. Instead of being negative feedback, it would be positive feedback. That pretty much wipe your control system, your attitude stabilization out very quickly. So if they saw that the attitude errors were growing instead of shrinking, you could hit the red button and switch this. That's a worst case, right? That you don't even know if it should be a +2 or a -2. So anyway, on-orbit tweaking is everybody does that. Hubble does that. I mean, we did it. You can usually get at least an order of magnitude better once you see what the actual behavior is and you trim that control algorithm. And many times I've heard stories of 100 times better, 1,000 times better. You just can't know everything on the ground, but watching how the attitude is evolving and seeing the fluctuations in the errors and seeing what frequency those errors, are they happening at orbital frequency? Are they happening at, whatever it is, you're going to be able, that's this disturbance torque that's bigger than we thought it was going to be. And so we're going to increase the gain on that part. And you slowly damp those oscillations down. And that can go on for years after the thing is in orbit. So I just made, I don't know, for fun slide of assembly, integration, and test. I don't know, I just threw it in here because the pictures were pretty, slide number 40. But I also threw it in to mention that this is a part that we designer types kind of a little bit take for granted. And when you watch the film on building a satellite, this is a lot of what you see. Just putting it together is a gigantic job, particularly for a big geosynchronous satellite. And your stuff is somewhere in there, you know what I mean? And so just framing your problem, where are the thrusters? Where's the CG? Do they have a clear field of view? Where are my sensors going to be? Because you may want to be on axis, so does everybody else, So it doesn't mean that you're necessarily going to be on axis. The system designers are going to tell you where your sensors are and which way they're pointing, and you got to pretty much, live with it. So, okay, basically this is the last slide, simplifying the attitude control sensors. That's what small satellite building has been all about. And of course, it's lost now in the sands of time. But the revolution of small satellites was simplifying, getting rid of everything but the necessary. So there are some sensors that are simpler than other sensors. A star tracker is, you can buy them. They're cheap now. We, sold ours commercially for a few $1,000s. Okay, that's a lot compared to your budget. But for a normal satellite, little satellite commercially built by Boeing or something, they're going to spend millions of dollars on that thing. So, if you tell them the sensor's $5,000, they're going to not trust you because the price is too low. Magnetometers, are super cheap, right? You can buy a nanotechnology magnetometer. There's one in your cell phone. So there's one in your GPS receiver. So, they're just a little, fraction of a sensor chip that might be packaged with accelerometers and other, motion sensors like your phone has to tell you, which way down is so that the screen always aligning itself to the way you're holding the phone. Okay. These are kind of small points, and to go through all of them might be fairly boring for you. So I just want to, kind of say, what can I summarize for all this? It always starts with managing the payload. And it was actually very interesting to me when Bowen sends me an email. She has a quote at the bottom which basically says, never accept requirements. Because if you accepted the requirements, that would be to say that they're already perfect. I mean, that's a fantastic, I live by that. It's so interesting to me to see it as the, kind of like signature line on Bowen's email, because that's where I get started as a system designer. Don't tell me how to do it. Tell me what you want to do. Customers are not used to that. They're used to telling you, okay, I need 0.1 degree angular, stability. That's a nice number. It's hard to get to with a little satellite. Then I always want to know, why do you think you need that? And they're going to tell you, well, because our pixels are this and that, or because we have to resolve something. So it's like, okay, do you have to hold 0.1 degree angular resolution for 40 years or for a millisecond, while you snap the picture? Those are two completely different problems. One is a rate problem. If all you need to do, right, do you need to have that angular stabilization physically, or do you just need to know your angle so that when you take the picture, you knew what you were looking at so you could line up the bits? They hate you when you start asking those questions. They're like, this guy is what they will call a real engineer. All these biases against engineers, that we're nitpickers, that we're, too immersed in the details. But the interesting stuff is many times, I'm not really that much of a, detail guy. But the interesting stuff is when you start to scrape away at the payload and what they think they want. So there's various things, that you can do there. So, and obviously, there's simpler modes. Like with that example, if you can afford to spin even very slowly, man, you're offloading huge amount of hassle. Wheels, power for the wheels, controller for the wheels, sensor for the wheels. What do you do if the wheel fails? A lot of times these little wheels are great. They're cheap. They don't weigh much. Of course, they don't have much angular momentum, so they're only going to work in a very small satellite. But they're noisy and they vibrate, and they mostly don't last very long. So, okay, if you're doing a CubeSat like Equisat, it's going to be in space for a couple of years, almost 3 years in that case, 2.5 years. It'll last. It probably won't die. But then you might get paranoid. If it dies, the mission is over. Maybe I should fly 2 of them. How much does it weigh? How big is it? Get rid of that whole thing by spinning the satellite. But then someone could say, well, if I spin the satellite, then I have to have a moment of inertia, maximum. If I'm flying a CubeSat, how do I do that to make the CubeSat? Okay, it becomes a strain on your mass distribution. Maybe the easy answer is, I'm going to put the batteries on a belt that goes around, on the 4 sides of the satellite. I'm going to have, that's the heaviest thing, and I don't care where they are, so I'm going to put them right behind, right on the walls, let's say, which could be a little risky because the walls get hot and cold and the batteries don't like it. But, whatever the millions of trade-offs, the millions of arguments that go on without end in the fluorescent lit, conference rooms of every company in the world. So, I like air core torque coils as an actuator because, obviously there's no expendable. You're just using electricity to make an electromagnet. And the reason I say air core is if you put an iron core in, like you would think would be much more efficient, and it will be 10 to 100 times more efficient, that iron core will magnetize, and then when you shut the electricity off, you have a permanent magnet. So then you got to think, how do I get rid of that permanent magnet? Well, I've got to run the current in the opposite direction. Then I'll change, the core to the other direction, but weaker. And so I'll build a little oscillator. When I shut it off, it'll oscillate back and forth and back and forth. How do you know that is actually going to work? You're going to have to test it on the ground. You're going to have to build that circuit. It's going to confuse your attitude control system because you don't just shut it off. You go into this oscillating mode to cancel out. So, okay, people have worked that problem out. But if you're just building a cheap little satellite, you don't need much torque, and an air core would be simpler. So there's a lot of little, tricks, like I talked about earlier. Sometimes a single wheel, you can only control one axis, but you're stable on all 3 axes because of the rigidity of the wheel. And maybe that's good enough. You can control the other axis with torque coils and slowly torque the wheel around if you don't have to make big excursions on the other axes. You can do that. Okay, so attitude determination versus control, the little green box at the bottom. What I was just saying, controlling the attitude is hard. Measuring the attitude is easy. And many times that'll be good enough. Or measuring to high accuracy while controlling to a lower accuracy. That is more often what happens. So, of course, if you have wider field of view instruments, just throw more pixels at it and look at a bigger piece of the sky, even though only a part of that sky is interesting to you. That's how the nature cameras work. That want to catch a fox going by or something like that they put in a box and leave in the field somewhere. They have a super wide field of view. They don't know where the fox is going to be, but they also have an excellent camera in them with lots of pixels, a nice Nikon reflex camera with a wide angle lens. So even though the fox will be relatively small, or the bird, or whatever it is you're trying to catch, you have enough pixels to do what you need to do. That's a lot easier. If you only have a narrow field of view and you're going to resolve super good, you've got to still have a wide field of view to point the narrow. You need a finder scope, like they have on a telescope. If you just take your high-powered telescope, what are you going to see when you look up in the sky? Nothing. You're going to be staring at black, and it's like, okay, where's Saturn? The finder scope is super wide field of view. You see Saturn, oh, it's over to the right in my finder scope. And so once you get it centered in the finder scope, you can switch over to the, more powerful telescope. And then the passive systems, particularly the unstabilized or aerodynamic or, whatever. And then I have this last slide, 42, which is, kind of, a little bit self-evident. Okay, believe it or not, we're finished. It took me longer than I thought I was going to take, but, I hope it was worth it to you, this whole big, long excursion into guidance and control. It's sort of as told by, a grizzled veteran. I'm not quite grizzled, but, I've been through so many programs ranging from the super complex to the super simple. And the one thing I'll leave you with is that people in the outside world will think that because you're building a little satellite, it's easy. It's simple. That is not true. Because on a big satellite, you have thousands of people to share that work. Your job at your desk is what it is, right? And when you have a small satellite, you have the 10 of you having to handle every single problem. And there may be one radio person and one attitude control person and one, mechanical systems person, one thermal person. And man, that's a lot of work, because in a big program, that work is divided among hundreds of people. And many of them have done it all their lives, and they're super good at it. And you enter the company, and they're like teaching you how to do it. Whereas, students build a little CubeSat. I have a lot of respect for that. It's super difficult. You don't know what you're doing. You're learning it as you go. And, it's kind of like somebody hands you a piece of music, or, this will happen to me when I'm playing. It's like, Rick, do you know this song? Can you play this song? Many times I do not know the song, and particularly here in Italy. So then they'll say, well, I'll sing a little bit of it for you. And it's like, really? You have to make that sound, decent. Or, you go plunging into your tablet and find it in the cheat books, and every song in the world is in those books. You got to have a little engine to, find it, but you do. And then you're looking at this piece of sheet music you've never seen before. And I've seen, particularly pianists who are really good at that. And they can just look at that and make it sound like they've actually been practicing it. That's one of the hardest things to do. And, that's what you're doing. It's really hard to do. So, you feel like it. You feel like you're really working. And plus, there's nobody to turn it over to. There's nobody to say, well, my kid's birthday, I'm going to take the day off. There's like nobody to hand the work over to. Can you do this? And when you have to be out, I'll take it over. No, there's no back. There's, it's not a relay team, where, there's many, many people. If you swim a little slower, somebody else can make it up, what you hope, right? Everybody's got a bad day. So, but you're the only one doing, the, whatever it is, subsystem, the power subsystem. It, pretty much, lives or dies based on what you're doing. So I try to make that distinction when I'm talking to people about small satellites. This is not easy. It's simple in the sense that the systems are much simpler, but it's not easy. There's a big difference between simple and easy. If you want to be a really good bike mechanic, bikes are a lot simpler than cars. But it's not easy. You're going to handle every system on that bicycle. There's a lot to know. Okay, hope you enjoyed it, and I'll be talking to you about the next topic, probably radios, soon. Bye-bye.